In this module, we are going to start a new topic in stochastic processes known as renewal processes. Of course, we have seen a very special case of that when we studied Poisson processes. So, general renewal process is essentially a counting process. Recall that counting processes were defined like this. You have successive arrivals taking place at random points of time, and then a counting process simply keeps note or record of how many arrivals took place up to time t. So, that is how the process evolves. So, essentially any counting process would be entirely distributionally determined by the joint distribution of the successive arrivals. Now, a renewal process is a special case of that, where the arrival times are assumed to be partial sums of an IID sequence of the so-called inter-arrival times. In other words, you start with a sequence of IID non-negative random variables, look at the corresponding partial sums of sequence. So, use those as the successive arrival times to define a counting process, and there you go, you have a renewal process. But remember, the IID inter-arrival times could have any distribution. The only assumption that we make is that these are not degenerate at 0, although taking the value 0 is allowed, called renewal processes. So, this is the first module in renewal process. So, let me define what a renewal process is. You have already seen a special case of a renewal process through Poisson process. We will come to that later, but let me give a general definition of a renewal process. It is a counting process, of course, counting process, but the thing is, it is a special counting process where the inter-arrivals are IID. So, remember, a counting process is completely driven by, you have these random arrival times, and then a counting process simply counts the total number of arrivals up to time t. That is how the counting process evolves. But there was no, you can have any model for the successive arrival times. So, renewal process is a special case where the successive arrival times are assumed to be partial sums of IID random variables. So, in other words, counting process with IID inter-arrivals. So, as said, the inter-arrival times are denoted xn, n greater than or equal to 1. They are IID non-negative random variables. Now, at this stage itself, let me make it absolutely clear that it is only assumed that xn's are IID non-negative random variables. We are not making any assumptions as to the nature of the common distribution. Could be discrete, could be continuous, could be a mixture of continuous and discrete. And secondly, they can take the value 0 with positive probability. So everything is possible. Okay. So, the only restriction is that they are IID non-negative random variables, and of course, to keep things away from triviality, we will assume that they are not degenerate at 0, because in that case all arrivals would take place clubbed at 0. So, there is a positive probability that xn's take positive values, but there is, you allow also the positive probability for taking value 0. So, anyway, so these are the inter-arrival times. Arrival times are going to be as expected, partial sums of this. For the sake of completeness, we put S0 to be 0, as we did even for general counting process, and Sn is the partial sum of this IID sequence. Since the xj's are non-negative, these Sns satisfy the usual requirement for counting process, namely S1 is greater than or equal to 0, S0, S2 is greater than or equal to S2, etc., etc. So, this is where the assumption that I just pointed out comes. We assume that probability that x1 equal to 0 is less than 1. So, that means the x's are not allowed to be degenerate at 0. So, with this assumption, it is not difficult to see that Sn goes to infinity with probability 1 as n goes to infinity. Well, how do we argue it? You can either argue it from Borel-Cantor lemma. How? Because since probability that x1 equal to 0 is less than 1, therefore, probability that x1 is positive. In particular, you can take a fixed quantity epsilon such that probability that x1 greater than or equal to epsilon is positive, so let us say alpha. Then the series probability xn greater than or equal to epsilon would be the same as, because their common distribution is the same, so that series would diverge, and that would tell you from Borel-Cantil lemma that with probability 1 the xn's have to be greater than or equal to epsilon for all but finitely many n's, and in that case sn's, the sums of these would have to converge with probability 1. Or you can also argue it from SLN, strong law of large numbers. Anyway, so since Sn goes to infinity with probability 1, remember that that was one of the assumptions, basic assumptions in the general counting process. Now here it's a consequence of our assumption that x1s or the x's are not degenerate at 0. So as a consequence, what happens is that the set of n's greater than or equal to 0 such that Sn is less than or equal to t, for any fixed t positive, this set is a non-empty finite set. And therefore, as for a counting process, we can define for every n t greater than or equal to 0, nt to be the maximum n such that Sn is less than or equal to t. So it's clear that what it represents is that number of renewals, arrivals, whatever you want to call it, up to and including time t. The only thing to remember that we are allowing more than one arrivals at the same time point, because xn's can be 0 with positive probability. So this process nt is called renewal process with, of course, IID interarrivals, which are represented by the xn sequence. So different xn sequences would give you different renewal processes, that's all. Now it is clear from the definition that the event Sn less than or equal to t happens if and only if nt is greater than or equal to n. The nth arrival less than or equal to t means, or the same thing as saying that up to time t there has been at least n arrivals, and therefore by going to the complement, this Sn greater than t happens if and only if the number of arrivals up to time t is strictly less than n, or same thing as saying less than or equal to n minus 1, because nt is only taking integer values. And of course from definition it's also clear that S sub nt, which is the time of the arrival of the last arrival up to time t, that time has to be less than or equal to t, and then by definition Sn t plus 1 has to be strictly larger than t. Okay, some notations. Let f denote the cumulative distribution function of the common cumulative distribution function of the interarrival times. So CDF of x1 is good enough. And let's say mu denote the mean or expectation of this distribution f. So you can think of it as mean arrival time. A word of caution here, we are not assuming that this mean is finite at this point. So mu could be infinite, that's allowed. Okay, and another notation that we are going to see is a simplifying notation. So Fn represents f convolved with itself n many times. So what that means is essentially that if you look at x1, x2, xn, IID with common distribution f, look at the sum of x1 plus x2 plus etc. xn, that is Sn, Fn represents the cumulative distribution function of Sn. Another very important or very commonly used notation, and that is f bar, it is just 1 minus f. This is often called the survival function. Okay, observe that for any n, since the event nt greater than or equal to n and the event Sn less than or equal to t are identical, therefore the probabilities are same, and since Sn goes to infinity, the probability that Sn less than or equal to t goes to 1 as t goes to infinity, because Sn goes to infinity. So no, here we are taking t going to infinity. So since Sn is a random variable, as t goes to infinity, probability that Sn goes less than or equal to t of course goes to 1. That's the distribution function of Sn, and that means that probability nt greater than or equal to n goes to 1 as t goes to infinity. But this is true for every n greater than or equal to 1. So you can, from that you can deduce that with probability 1, as t goes to infinity, nt actually goes to infinity, because the probability of nt being bigger than or equal to any n goes to 1 as t goes to infinity. So as t goes to infinity with probability 1, nt has to go to infinity. Here is a very, very important quantity that will play a huge role in the entire mathematics of renewal processes. MT. So MT is expected value of NT, or expected value of the number of arrivals up to and including time t. This is called the renewal function. One thing is immediate from the definition is that MT increases with t, because NT increases with t. But on the other hand, you can write MT equals to the sum of the series n equal to 1 to infinity f and t for every t greater than or equal to 0. Why is that so? That is so because see, this is a nice formula for expectation of a non-negative random variable or non-negative integer valued random variable. Expected value of a non-negative integer valued random variable is the sum of the tail probabilities. So that's what we are using here. MT is the expected value of NT, but then since NT is a non-negative integer valued random variable, the expected value can also be obtained by taking the sum of the probabilities that NT is greater than or equal to n. But NT greater than or equal to n is same as the probability that Sn less than or equal to t, and that we have denoted to be Fnt. The CDF of Sn is Fn. So that gives you this formula that MT is summation Fnt. Okay. A natural question is MT finite for all t? Not clear. We know that NT is finite. There can be only finite number of arrivals in a finite time t. So NT is finite, but there is no reason to immediately conclude that expected value of NT has to be finite, and this is not even clear from this formula. Well, the answer happens to be yes. In fact, we will show that, the proof that we'll give will show that MT is not only is MT finite, that is, not only is NT has finite expectation, NT actually has finite moments, all moments finite. Anyway, the answer is yes, and we show this by using a very, very interesting technique, which is not just used in this context, but this technique has proved to be very useful in many, many different contexts in probability. The crux of the idea is to construct a new process which is simpler to analyze and at the same time comparable to our original process to yield the desired result. So we want to show that expected value of NT is finite. We would construct a new process which is much simpler, and therefore it's easier to compute the expected value of that process, but at the same time this simpler process is comparable to the original process NT, so that by drawing some conclusion about that process, we would be then able to conclude or make an inference about our process NT. That's the whole idea. Well, you will see what we mean by this. So in this specific context that we are dealing with, this is going to be achieved by constructing a new renewal process which has shorter interarrival times than the given one, thereby meaning that for that renewal process there are likely to be more arrivals up to time t compared to our NT. So if that has a finite expectation, then our thing would also have finite expectation, and luckily the new renewal process that we would construct, you would be able to explicitly calculate the expectation and show that it's finite, and not just expectation. As I mentioned, we would be able to also actually show that all moments are finite, which will then in turn show that our renewal process also has all moments finite. Anyway, so let's get on with that. So first choose an alpha positive. So I'm about to construct that new renewal process, simpler one. So choose alpha positive such that f alpha, I'm going to call it p, is strictly less than 1. Now that's possible. Why? Because recall we assume that f0 is less than 1 and f is CDF, so it's right continuous. So as x goes to 0 from the right, fx goes to f0, which is strictly less than 1. So I should surely be able to find some alpha close enough to 0 but positive, such that at alpha the value of f is less than 1. So that's how we choose alpha. Now here is our new renewal process. So the original renewal process NT had interarrival times xn. We now define a new renewal process to be called n hat t, whose interarrival times are yn, which is defined this way. So let's look at this definition. So what is yn? When xn is greater than alpha, yn is alpha. when xn is less than or equal to alpha, yn is 0. So yn takes the value 0 with probability p, because p is the probability that xn is less than or equal to alpha, and it takes the value alpha with probability 1 minus p. So the new renewal process that we are going to construct, n hat t, has interarrival times which takes only two possible values, alpha or 0, with probabilities p and 1 minus p, where p is positive. And moreover, yn is by definition less than or equal to xn. Why? Because when xn is greater than alpha, yn is alpha, and when xn is less than or equal to alpha, but of course it cannot be less than 0, yn is 0. So yn is always less than or equal to xn. So yn, as I said, yns are IID random variables taking value 0 and alpha with probabilities p and 1 minus p, and this is exactly what I stated. So for all n greater than or equal to 1, yn is less than or equal to xn always, which is exactly what we said. Though this new renewal process n hat t has interarrival times which are shorter than the interarrival times of the original n process, and therefore n hat t is always going to be larger than or equal to nt. So for this new renewal process n hat t, call the renewal function m bar t. So this is exactly what we said, that since all the yns are less than or equal to xn for n greater than or equal to 1, that would clearly imply that n hat t is greater than or equal to nt for all t greater than or equal to 0, which would of course imply that m bar t is greater than or equal to mt, and our aim is to show that mt is finite. We would achieve this by simply showing that m bar t is finite. So we'll show that m bar t is finite. This will show automatically that mt is finite, and in fact, as I said, we will be actually able to compute m bar t explicitly. So now the computation starts. Observe, since each yn can only take values 0 or alpha, for the n hat t process, arrivals can occur only at times which are multiples of alpha. Of course, since yn can take the value 0 with probability p, it's possible to have more than one arrivals at any such time. So two things. One is the interarrival times of the n hat t process can take only two values, 0 or alpha. So arrivals for the n hat t process can only occur at these times which are multiples of alpha. And of course, it's possible to have more than one arrivals at any such time. Now for n greater than or equal to 0, let us denote Zn to be n hat n alpha minus n hat of n minus 1 alpha. So this is the exact number of renewals at n alpha for the n hat process. What is the distribution of Zn? Well, this picture would give you some idea of what Zn's look like. So this is the path of the n hat process. So if you had looked at the picture, you can convince yourself. This is what happens. Arrivals at time t equal to n alpha start with one arrival of length alpha, because the arrival, suppose there is an arrival at n minus 1 alpha. Now all successive arrivals of length 0 would keep on happening at n minus 1 alpha until such time that there is an interarrival of length alpha, when the first arrival at t equal to n alpha will start. So arrivals at t equal to n alpha start with one arrival of length alpha after all the arrivals at time t equal to n minus alpha has been completed, and continue with all the subsequent arrivals of length 0 prior to the next arrival of length alpha, which would be counted, that arrival of length alpha would be counted as an arrival at time t equal to n plus 1 alpha. So here is one way of thinking about it. So we are interested in the distribution of Zn. There is a number of arrivals of the n hat t process at time t equal to n alpha. Consider independent tossings of a coin. Heads probability is p, which is the probability that y1 is 0, and tail probability is 1 minus p, which is the probability that y1 is alpha. Then each Zn counts the number of tosses starting with a t prior to and not including the next t. So Zn counts the number of tosses, number of arrivals starting with an arrival of length alpha, interarrival of length alpha, prior to the next interarrival of length alpha. That's exactly what it is. Then you can easily see, I mean, number of tosses starting with a t prior to but not including the next toss, next tail. Of course, that's a geometric distribution with parameter 1 minus p, and expected value of this Zn is 1 over 1 minus p. So it's as simple as that. Okay, so now let t greater than or equal to 0. Suppose k is, we were supposed to look at n hat t for a general t, although arrivals for the n hat process happen only at n alpha times which are multiples of alpha. So what we do is this little algebra. So for any t greater than or equal to 0, take k such that k alpha is less than or equal to t less than k plus 1 alpha. So k is the integer part of t over alpha. Then nt is nothing but, or n hat t is nothing but sum of the Zn's from n equal to 0 to k. So m bar t, which is the expected value of this, would be k plus 1 divided by 1 minus p, and that is because there are k plus 1 any terms starting from n equal to 0 to k, and each Zn has expectation 1 over 1 minus p, so it becomes k plus 1 over 1 minus p. And by definition of k, you can see that k is less than t over alpha, because it's an integer part of t over alpha, so it's less than or equal to t over alpha. So k plus 1 is less than or equal to t plus alpha over 1 by 1 minus p. In particular, we have shown that m bar t is finite, from which it follows that mt is also finite. Now, as I mentioned, you can easily see from this that since n bar t is a sum of, for any t, is a sum of finitely many geometric random variables. So in fact, n bar t, n hat t, has all moments finite, and from that you can conclude the same is true of nt for all t. Next is something that we have seen already. Poisson process is a very familiar example of a renewal process. We already saw that, so it's just quickly recalling that. For a homogeneous Poisson process with intensity lambda, we know that interarrival times are IID exponential lambda. In other words, Poisson process with rate lambda, as was defined, turns out to be a renewal process with IID exponential lambda interarrival times. In fact, this gives one of the equivalent definitions of a homogeneous Poisson process with rate lambda. To be precise, so this is something we have seen. Definition of Poisson process as a renewal process. So let x1, x2, etc. be IID exponential lambda. Consider the renewal process nt t greater than 0 with xn as interarrival times. Then nt is a homogeneous Poisson process with intensity lambda. Now this is nothing new, we have already seen it. We have seen that one can start with this definition and show that the condition of the other definition are satisfied. So this is just to point out that Poisson process, which we have already studied, is a special case of a renewal process. Okay, let's quickly look at a few basic things about renewal process before we, in the next module, will move on to a little more detailed analysis. So the thing that we want to quickly take a look at is what happens to nt. Well, we have already seen that nt goes to infinity as t goes to infinity with probability 1. What we want to ask is, at what rate? Does it go to infinity at the rate of t square, e to the power t, or root t? So we'll get a quick result on that. Denote expectation of x1 to be mu. Note that mu has to be strictly positive because x is not degenerate at 0, but mu could be plus infinity. So that's something that you should keep in mind always, that even though we are denoting e of x1 to be mu, I'm not assuming that mu is finite or that x1 has finite expectation. Notice that Sn over n goes to mu with probability 1 as n goes to infinity by strong law of large numbers. Now, at this point, you may wonder Don't we need finiteness of mean for strong law of large numbers? Well, yes and no. In general, you do need for strong law of large numbers. That is true when there is finite mean. However, in case of an IID sequence of non-negative random variables, SLRN holds even if the common mean is infinite. That is, in case your SNs are partial sums of IID sequence with plus infinity as a mean, then Sn over n goes to plus infinity with probability 1. Okay. Now we know that Nt goes to infinity with probability 1. Sn over n goes to mu with probability 1 as n goes to infinity. So looking at Sn along the subsequence Nt, we would get Snt over Nt would converge to mu with probability 1 as t goes to infinity. We also know that since Nt goes to infinity with probability 1, Nt plus 1 over Nt has to go to 1 with probability 1. That's basic calculus. This would imply that if I look at Snt plus 1 by Nt, then you can write it as Snt plus 1 over Nt plus 1 into Nt plus 1 by Nt. The second factor goes to 1, the first factor goes to mu. So Snt plus 1 divided by Nt goes to mu with probability 1. But remember that Snt is less than or equal to t less than or equal to Snt plus 1. So that implies, of course, that Snt over Nt is less than or equal to t over Nt less than Snt plus 1 over Nt. Now what does all that lead to? Well, that's what we'll say next. We already know that Snt over Nt as well as Snt plus 1 over Nt, they both go to mu. So that would mean that t over Nt goes to mu. Mu could be infinite, mu could be finite, but t over Nt goes to mu with probability 1 as t goes to infinity. And in either case, whether mu is finite or infinite, you can always go to the reciprocal and therefore claim that Nt over t therefore goes to 1 over mu as t goes to infinity. Here 1 over mu has to be interpreted as 0 if mu is infinite, and of course it's a positive quantity if mu is finite. So in particular, if mu is finite, in which case 1 over mu is a positive quantity, that means that in that case when mu is finite, Nt over t goes to a positive quantity as t goes to infinity. So that what that means is that Nt goes to infinity as t goes to infinity with probability 1, but Nt over t goes to a positive quantity. So what that means is that Nt goes to infinity roughly at the same rate as t. So this is just initial analysis, basic elementary analysis. We are going to dig deeper into this issue and see some more intense results, finer results along these lines. So in this first module on what is called renewal processes, what we essentially did was we first defined or introduced the notion of a renewal process, namely its interarrival times, laid down the basic assumptions. In particular, the only one assumption that we made apart from the fact that the interarrival times are IID non-negative random variables, the only assumption that was made was that the interarrival times are not degenerate at 0, which of course immediately forces that the arrival time sequence has to blow up to infinity, which made a definition of counting process possible. So then having done that, we saw that if we define the renewal process as Nt, then Nt goes to infinity with probability 1. And then we saw that if we define what is called a renewal function, which is going to be very, very important in the context of renewal processes. Renewal function is simply it's a function of t called mt. We defined that, and it's simply the expected value of nt, which is the expected number of arrivals up to time t. Of course, there is no reason in general to believe that this should be finite, but we did prove actually by a very interesting technique of constructing a simpler renewal process which is comparable to this, but at the same time it's much simpler to analyze and compute. So we were able to show using that comparison that any general renewal process, the renewal function is finite. That means Nt has finite expectation. And then towards the end we showed, we know that Nt goes to infinity as t goes to infinity with probability 1, but we showed that Nt over t goes to 1 over mu as t goes to infinity with probability 1, which in particular would mean that if mu is finite, in which case 1 over mu would be a positive quantity. In that case, that says that with probability 1, Nt not only goes to infinity, but it goes to infinity sort of at the same rate as t. So we'll explore this a little bit more in the next module.